Hello all, welcome to CyberCrete, and in this video we are going to see the logarithmic time complexity. And if you are someone who is just so scared of the logarithmic and does not understand what does this log mean, trust me, after watching this video you would have the complete understanding of the logarithmic and you won't be scared anymore. With that said, let's get started. So here on the screen you can see that I have written some bunch of formulas. So here you have your logarithmic formula. Like log of x with the base b, this we basically read as base, is equal to y if and only if, so here I am trying to write if and only if b of y is equal to x. So what does it actually means? So it actually means this b is just going to come here, this b is just going to be represented here, and this y is just going to come up here. So what does it mean intuitively? So here it just means that by which power are you going to raise your base. Here we are just raising our base with the power that we are going to get the certain number x. And if you are someone with a math background, then you must be told that if we are just simply given the log of 20, we are just simply going to assume that the log have the base 10. But here in the computer science we always take the base as 2, or you can say that the binary base, because in the computer science we only deal with either 0 or 1, and that is the reason why we always take the base as 2. So whenever in the time complexity you ever see the log is just written as log of n, you are basically going to assume that it have the base of 2. So with that said, we are going to see this. So log base 2 of x is equal to y if and only if you are going to raise the base 2 with the given y such that you are going to get the n. So here we are writing n and here we wrote x. This is basically the math formula, but this is our computer science formula. So here you can clearly see that by which power of 2 we are going to raise this y to get our number n. So this will become more clear once we are just trying to derive into some of this example. Like if we are trying to find the log of 1, so how we are going to find this? To find this, we are trying to ask us a question. So what question are we going to ask? The question that we are going to ask is that by what power of 2 we are going to increase it so that we get 1. So if we are trying to just increase the 2 with the power of 0, we are basically going to get 1. So that is the reason why the log of 1 is going to be 0. So let us understand it by one more example. So if you are given to find the log of, let's just say 4, so here how you are going to find this? So here you are also going to ask the same question, by which power of 2, so we are just going to write the 2, by which power of 2 we are going to raise it that we are basically going to get 4. So here you can see that if we are going to just raise the 2 with the power of 2, we are going to get 4. So here we can simply write log of 4 is nothing but our 2. And the same if we are going to do with our log of 16. So what is going to be our answer? So log of 16 means for what power of 2 we are going to raise it such that we are going to get 16. So if we are going to raise our 2 with the power of 4, we are going to get 16. So here we are simply going to get our answer as 4. And here we are taking the 2 because in computer science you are always going to take 2, as in computer science only we work with binary 0 and 1, and that is the reason why we are working with the base of 2. So here what is happening intuitively? So here whenever we are increasing the power of 2, then we are simply just multiplying this number by 2, or you can also say that we are just doubling the number. So here you can see that the log of 4 is basically 2, and if you are going to find the log of 8, it is basically going to be 3. So here you can see that when we are just increasing our log number just by 1 from 2 to 3, we are just doubling our 4. So as soon as you double this 4 to 8, we are simply going to get just a single increase in our log number. So let me show you, like log of 2 power 4 is nothing but your log of 2 power 3 into 2. So here we are just multiplying our previous log with our number 2. And if you have paid attention in logarithmic, this is the most interesting part of our logarithmic. When we are just trying to double our input, so as we are just doubling our input, it is just going to increase by 1. So let's just say you have 100, and if you just double this 100, so 100 into 2, it becomes 200, then your log is just going to increase by 1. So this logarithmic is very interesting property, which basically says that as you double your number, your complexity is just going to increase by 1. So if you have seen the chart of our logarithmic and our log of n, you can basically see that this is our chart, and if this is our n, the log of n will be something like this. So as soon as we are just doubling our input, our log is just increasing by 1. So every time you are just doubling your input, your log will just increase by 1. So this says that if your number is increasing rapidly, your log is basically going to increase too slowly. So let me prove this with an example. If you are going to find the 2 power 20, it is basically going to be around 1 million. But when you just increase your 2 power 30, this will just give you 1 billion. So here you can see that 1 million and 1 billion, there is very huge difference between these. So here you can see that you just increase your 20 to 30, and you can see that there is huge difference between their resultant. With 2 power 20 you are getting 1 million, with 2 power 30 you are getting 1 billion. So from this example you can basically see that when the size of n will increase rapidly and too fast, the log of n is basically going to just increase tiny bit. So when you have very large input, the log of n will be very less. So let me explain you more with the help of an example using a simple array. So let us basically take an array of size, let's say 8. So you have basically 8 elements in your array. So this is of 8 size. So let me just quickly write the number. So it is 0, 1, 2, 3, 4, 5, 6 and 7. So as you are starting your index from 0, it is still 7. So there are 8 elements in our array. And suppose that you are just going to take an algorithm that is basically going to divide this array into half, and then it is basically going to just look throughout this array, not this one. So it is just going to completely neglect this array, and in the next step what it is basically going to do, it is just going to again divide this array into 2 halves. So again it is not going to see this part, it is just going to see this part, and again it is basically going to divide this array into 2 parts, and it is just going to look this part. So here with the array of size 8, we basically have to perform 1, 2 and 3 operations. And let me just increase the size of our array with 16. So let us just suppose that our array contains 16 elements. So if we have 16 elements, the first thing that we are going to do is we are basically going to divide this array into 8 and 8 each, and then we are not going to look throughout this array. So it is 8, and then our problem just became same as this problem. So here we basically have 8 elements. So again we are going to perform the same action. So we are basically going to divide it into halves, that is 4, and here is 4. Then we are just doing it with 2. Then we are just basically going to do with 1 element, and we are done. So here the total number of steps that is increased is just this one, and rest are same. So this 1, 2 and this 3 are same, and we just have our one step that is increased. So here we can see that we have just doubled the size of our array, but the total number of steps that is required to perform is just increased by 1. So by this example you can clearly see that how useful this log of n is. So if you are having an algorithm that is having the time complexity of log of n, then you have come up with a very wonderful solution, as it is much better than your big O of n solutions. And one more common example of this log of n is in our binary tree, if you have ever heard of it. So let me simply draw it. In binary tree what we do, we just have a tree like structure of nodes like this, and then we again have the nodes here. And in our binary tree what we do, when we are basically trying to search for any element, then we are basically just looking at this value. Then by looking at just this value, we know that either we have to go this side or we have to go this side. So once we decided to go this side, we are just going to eliminate this all. So we are not going to look at this part, and again when we come here to this, we basically check if we have to go this side or if we have to go this side. So if we know that we have to go this side, we are just going to look this part, we are not going to just look this. So here we can also see that this operation is just taking the log of n time, because we are just eliminating the half of our workload in every single step. So if you need to find that whether or not your algorithm is going to take the log of n time complexity, the only one thing that you have to ask yourself, that if we are just somehow decreasing our operations by half in every steps, like on the binary tree we have seen that we just decrease our number of steps by half in every step. Or you can also check it by, if you are just doubling the size of your n, we are just multiplying it by 2 or just double it, then the total number of steps that you are going to take is just going to increase by 1. So if you meet any condition like this, you are basically going to tell that the time complexity of your algorithm is nothing but your log of n. So that was it for this video, and I think that this log of n is basically clear to all of you and you are never going to forget it. And if you just have any doubt left in your mind, you can just ask me. And that is it for this video, and I will meet you in the next video where we are basically going to talk about the space complexity. So thanks for watching.